Hello, my name is Jared Skeens, and welcome to the Zoom room. Today, we'd like to cover our Pure Maths 1, Quadratics, Part 4, Reducing to a Quadratic. So this reducing to a quadratic is going to be an important skill for you because not every equation that you run into looks exactly like this ax squared plus bx plus c equals 0 format that you're used to seeing when it comes to a quadratic. So what you're going to be looking for specifically are the exponents, the exponent pattern. So in our lead term here, we have a 2. This is what makes it a quadratic. So this is our quadratic term, or sometimes called a second degree term. This one here has an understood exponent of 1. That's our linear term. Then we have the constant term, or our 0 degree term, which is kind of like an understood x to the 0 power. And of course, anything to the 0 power turns into 1, which is why you can't see the x. So we have a 2, 1, 0 exponent pattern for a normal quadratic. Now, these examples up here actually aren't quadratics, but we can use our quadratic way of solving as long as these equations follow a multiple of the exponent pattern. So notice this is 2, 1, 0. When we look at this one here, it's 4, 2, 0. So in other words, it's a multiple of 2. So if we were to look at it, our 2, 1, 0 is now multiplied by 2, and we have a 4, 2, 0 exponent pattern. So if it is a multiple of the exponent of the 2, 1, 0 exponent pattern, then we can treat it like a quadratic. We can use all the different methods that we've learned so far in this unit on this equation because it follows the pattern because it's a multiple of the 2, 1, 0. If we look at this one over here, we have a 1. That's an understood 1. Well, let's put our pattern up first. 2, 1, 0. And here we have a 1, 1/2. Remember, 1/2 is the same thing as square root, power over index number. So when you see a fractional exponent, it's actually a radical. You can write it either way. Sometimes you might see minus 11 root x or minus 11 x to the 1/2. Same thing. You need to recognize the exponent as a 1/2 and then 0. So when you look at this, this is also a multiple. In this case, it's a multiple by 1/2. Okay, so it says reducing. Normally you think of reducing as like going smaller, kind of like this, go from big numbers to small numbers. But actually it can go either way as long as it's a multiple of our original 2, 1, 0 exponent set. That's what you're looking for. So at first, when you look at these two equations, you might like, that's crazy. We haven't learned how to do those kinds of equations. But because they follow these patterns, we recognize that. And that's going to be your clue because you're at the beginning of Pure Maths 1s. You don't get to polynomials until Pure Maths 3. So in other words, you're not going to get into cubic equations and these fourth power equations until Pure Maths 3. So whenever you see this in Pure Maths 1, it's high percent chance that you're most likely dealing with this reducing to a quadratic concept. Okay, so that's the first thing that should come to your mind. Look at the exponent combination, make sure it's a multiple. If it is, it means you can use anything from quadratics units. So actually, if you look closely enough, or I should ask you, do you think this factors? Maybe I kind of already you a hint. It does factor, but I won't tell you right now how it factors or how I know it factors. But it does factor, and if you can see that this factors, the factoring method would actually be the way to go. Okay, it's the more efficient way. Students don't always recognize when some of these, especially with the front term and back term with more possible factors to them, they don't always recognize an equation can factor. So I actually took the same problem and used the same coefficients with just different exponents. What I want to do, I don't want to redo the factoring. What I want to look at is in part 3, we looked at the quadratic formula and the magic potion. I want to do those side by side so that you can see both how either one can solve these equations and then what details we need to look for when we're doing a reducing to a quadratic, okay? So over here on the left, I'll do the quadratic formula, and over here on the right, I'll do the magic potion, okay? That way you can see both. So if you remember the quadratic formula, you have to memorize it, and it comes off of the completing the square principle. But all you need to do is remember the formula. You're going to have x equals, now I'm putting x, we need to discuss that at the end, okay? So I'm just following the formula right now. X equals a negative b. Well, our b term is a negative 11, so I'm going to put that in parentheses. Negative b plus or minus root b squared minus 4ac all over 2 times a. So there's our quadratic formula, a little bit lengthy. So now we need to simplify that, okay? So what I do is I simplify the radical first. I just work up here. Negative 11 squared is 121. Let's see here. 4 times 6 is 24. 24 times another 4, that's 16, 8, 96. So minus 96. And 121 minus 96, well, what do you know? That's 25. And the square root of 25 is 5. So we're looking at a plus or minus 5 there, okay? So what we're going to end up with here is positive 11 plus or minus 5 all over 8, okay? And this becomes 11 plus 5 over 8, which is 16 over 8, which is 2. And this becomes 11 minus 5 over 8, which is 6 over 8, which is 3/4. Okay? Now, I'm going to stop right there. We're actually not done. We followed the quadratic formula for x, but actually, we don't have the x. If you look at our original quadratic equation, the x in the formula is this right here. So that actually is our key, okay? So we're not done. I'm going to come back to this. What I want to do now is we have the same coefficients. Let's look at the magic potion method, okay? So if you remember the magic potion method, you have the midpoint. You find the midpoint of the roots, which is the opposite of b divided by 2. But before we do that, I'm glad I remembered. Remember with factoring, completing, you don't have to with factoring, you can if you want. With completing the square and with the magic potion, I said it's better to get rid of that a. We want to divide it through first, really quick. So that gives us x to the 4th minus 11 over 4 x squared plus 6 over 4. 6 over 4 is the same thing as 3 halves equal 0. Now, it might look scary because there's fractions. Don't worry about it. It's okay. So we start off with the midpoint. The midpoint is the opposite of b divided by 2. So the opposite of a negative is a positive. B divided by 2. Remember, when you divide a fraction by a number, it's the same thing as multiplying the number into the denominator. So if we're dividing this by 2, it's the same thing as multiplying by 1/2, where the 2 times the 4. So this is 11/8. You can do it on your calculator if you want to, if you're a little nervous about fractions. So the opposite of the b divided by 2, that was our midpoint, plus z, that's our symmetry, and then 11/8 minus z, again the midpoint going both ways from our axis of symmetry and the parabola, equals the c term, 3 halves. Okay, so now when we multiply this together, remember again, you don't have to do the nose and mouth, they cancel out. We just do these two up here. So 11/8 times 11/8 is 121/64 minus z squared equals 3 halves. Now, because this is in 64ths, I'm going to change this to 64ths just to make it better. So if this is 64, we have to multiply by 32. So if we multiply this by 32, we get 96. Again, you can use your calculator to help you with that so that you're not straining your brain. Okay, so if we add this to the other side and subtract this one over here, we get z squared equals 121 minus the 96 over 64. So we added z squared over here to make it positive. We subtracted the 96/64. They have common denominator. And what do you know? This gives us 25/64, which then becomes z equals, when you square root both sides, plus or minus 5/8. Interesting. Here you can see right here the plus or minus 5/8 in the quadratic formula. So we're really doing the same thing, but this method comes off of completing the square. This method comes off of your graphic version where you're doing symmetry from your midpoint, but ultimately you're going to get to the same thing. Now remember, the z is our symmetry. So we're not there yet. We need to add it to our midpoint. So our x is going to equal 11/8 plus or minus 5/8. So of course, 11 plus 5/8, that's our 16/8, which equals 2. Same answer as we got here. And then down here, 11 minus 5/8 equals 6/8, which equals 3/4. So we arrived at the same location, and our work here went up this way a little bit and down. This we divided by a first, worked our way down. So don't look at how many lines it is. What's important for you is which method you feel the most comfortable with. Okay, so both of them are equally valid. It doesn't really matter to me which one you use, but either you memorize the quadratic formula or you remember the midpoint and symmetry. What's important is that you can become efficient and successful at these question types. Now, we're not done yet. We didn't actually find x. Now, at this point, our two questions are going to diverge. If you notice in our ax squared plus bx plus c equals 0, when we go to the quadratic formula, we're coming from the value of x. X is what we're looking for. That is the key And this is what the quadratic equation solves for. When we look at over here on this one, it's actually a root x. So be careful that you don't stop here. You need to make sure that this isn't really an x, it's an x root x. So we need to take these answers. You can write it like this if you want. Same thing as x to the 1/2. Doesn't matter which way. One is exponential form, one is radical form. Equals 2. So, and root x equals 3/4. Now, here is where you're going to have to be careful. You're going to square both sides to get x. Okay, that sounds simple enough. And you get x equals 4, and you're going to get x equals 9/16. When you square both sides, I'll mention this again in the future. It's not a topic that you teach, it's just something that you run into that you need to be aware of. Just like right here, when we square rooted both sides, if you put the square root on here, square root both sides, you have to remember to put the plus or minus. That's just something you have to remember when you're dealing with roots. Well, the same thing when you're dealing with squaring both sides. You don't put the plus or minus, but when you square both sides, you have the chance of introducing what's called, let's see if I can remember. I call it the phantom number. Technically, it's not called the phantom number. It's called the extraneous root. Okay, let me, extraneous root. Okay, sometimes I call it the phantom number. What this means is this. I'll just do it. I guess I'll do it down here and then erase it. Let's say you have 4. There's 2 ways of getting that 4 when you square. It could have come from 2 times 2 to get 4, but it could have also come from -2 times -2. That can also give you 4. The question is, which one of these sets actually came from the problem? If it came from the problem, then this is a correct answer. But if this 4 came from what's called the extraneous root, meaning there's another way of getting it that's not from the problem, then your answer won't work when you plug it back in. So the bottom line is this: when you square both sides in your solving process, you need to take your answers, plug them back into the original, and see if they work. Now, in this particular case, they both do work, and so these are your correct answers. But notice your highest exponent is a 1, meaning, generally speaking, you would only expect to get one answer for your solution set. In this case, both of these do satisfy the equation and you keep both. But it is possible that one of those answers are not going to work. It won't come up to 0 when you plug it back in. If that happens, that means that your number came from the extraneous set, not from the problem itself, and you would discard that answer. Usually that's going to happen when you end up with a negative, I guess at this point, before you square it, if the number before you square it is negative, and then by squaring it, it becomes positive, that's kind of like your little red flag that you want to go bing, bing, bing in your head, saying you need to double check it. Since both of these were already positive and you squared it and they stayed positive, it's not a problem. But you should just get in the habit of double checking those when you square both sides. Just like when you square root both sides, you put the plus or minus. So a lot of students forget that very little detail, and it can affect you. I'll point it out at some point in the future when we run into it again. Okay, so that's this side right here. We finished up. These are the correct answers for x, because actually this one right here technically is not x. It's actually x to the 1/2. Okay, I'm going to erase this little bit here because the work over here took up the board. So I'm going to use this space. So over here, now notice we didn't use the quadratic formula, but I put my x in here at the end. So this actually isn't x. This now is x squared. Because remember, the magic potion method was an alternative method to the quadratic formula, meaning we're using a method that solves for x. But this equation means our method is actually solving for x squared. So technically, this should be x squared down here. So what I get is, I get x squared equals 2, meaning my x is equal to plus or minus root 2, and x squared equals 3/4, which when I square root both sides, x equals, and remember, see, I'm putting the plus or minus, so this would be root 3 over 2 because the denominator comes out. So we're taking the root of both sides because our key here is x squared. And when we root both sides, we put plus or minus. Here we're rooting both sides. The top stays as root 3, root 4 comes out as 2. Here are our answer sets. With square roots, you don't have to double check your answer like you do with squares. You do have to remember the plus or minus. Notice this is a 4th power, meaning we expect 4 answers, and that's what we get. Plus or minus root 2, that's 2 answers. Plus or minus root 3 over 2, that's 2 answers. We have a total of 4 answers. So here we have it. This is how you reduce to a quadratic. Here are 2 different examples using 2 different methods, and up to the point of similarity, we got the same answer. Then this one went with the root x, this one went with the x squared to get our final answers. But you're using the quadratic tools with these non-quadratic equations as long as they are a multiple of our original 210 exponent pattern. Okay, I'll set up and go over one more question that's maybe a little typical. Actually, this is a Cambridge question, but I'll give you another one so that you can see a little bit different perspective of how it's used in the Cambridge questions, and we'll see how you do. Okay, here we go with a Cambridge type question for this reducing to a quadratic idea. It says, find the coordinates of the points of intersection of the curve y equals x to the 2/3 minus 1 with the curve y equals x to the 1/3 plus 1. Wow, that looks scary. Well, first thing that you should recognize is, let's look at our question. You need to learn how to interpret the questions. They don't always give you just the equation and say reduce to a quadratic, or that. You're going to have to think how to get there. Now, when you first look at this, you're probably not thinking reduce to a quadratic. So I circle my verb, find. What am I finding? Coordinates. That means I need both x and y values. Another thing, points of intersection. Intersection means these 2 graphs cross. And if 2 graphs intersect, that means we're solving simultaneous equations. Now, I know you're thinking, wow, simultaneous equations in IGCSE material is a lot different than this. We didn't have fractional exponents. Well, you're going to have to get used to it, but the concept is the same. Now we got these 2 curves. We know that they intersect. So that means if y equals this and y equals that, and they intersect, then that means y1 equals y2, at least for the points of intersection. So That means x to the 2/3 minus 1 equals x to the 1/3 plus 1. Wow. Some of you are probably still intimidated by fractional exponents. Well, remember, this fractional exponent is the same thing as the cube root of x squared. Remember, power over index number. So a fractional exponent is the same thing as an exponent and a radical put together. Just like a fraction is both a multiply and a divide put into one fraction, same thing in the exponent level, it's an exponent and a radical in the fraction. So don't really worry about that. That's not what's important at the moment. What is important is how do we arrange this thing? Well, anytime you're working with polynomials, you want to arrange it in highest to lowest exponent order. So descending exponent order is usually how you want to arrange it. Now, sometimes there are certain things that you'll see in the Pure Maths 1 that they ask you to arrange it in ascending exponent order, but when you're working with polynomials in general, you want to go with descending exponent order. So 2/3 is bigger than 1/3. So we're going to move everything to the left. We're going to subtract our x to the 1/3 from both sides. Now notice you are not combining it with this. These are not like terms. To be a like term, you have to have same variable, which they have, but you also have to have same exponent. These are not same exponent, not like terms. So this becomes x to the 2/3 minus x to the 1/3. They are not like terms. Don't try to combine them. Minus 1 equals plus 1. Well, let's just go ahead and move that minus 1 over. These ones are like terms, so we get minus 2 equals 0. So you're able to follow that. We subtracted these two to both sides. Over here, you can see our little boundary. You do the same thing to both sides of the equal sign. The x to the 1/3 is not a like term, so it has to be separate. The ones are like terms. They combine to make minus 2. So when you look at this again, you're like, ooh, we got these nasty fractions in the exponents, and what do I do with this? Well, you should always remember when you're working with your non-normal polynomials that you're probably working with something that can reduce to a quadratic. Quadratics is a major thing that you work with throughout the Pure Maths 1. So assume that it is a quadratic. Well, let's make a little test. We know that our normal quadratics follow a 2, 1, 0 exponent pattern. And let's see what this has. This has a 2/3, 1/3, 0 exponent pattern. What do you know? All you're doing is dividing by 3. So it is a multiple. I said divide by 3. If you want to make it a multiple, multiply by 1/3. Remember, division is just the multiplicative inverse. So if you multiply by 1/3 or divide by 3, you get this similar pattern, 2/3, 1/3, and 0. So this is indeed an equation that we can use quadratic tools on. So that means the key is this one right here. This is our key in our solving process. Now, actually, like I said, you can use any quadratic tool that you want to. Yes, this does factor, and you should be working on your factoring skills. If you recognize that this can factor, then you should factor it. It is the more efficient method. When you factor it, instead of having x in your factors, you should have x to the 1/3. In fact, let's go ahead and do factoring since it is the more efficient method. I was going to do the magic potion again, but I've already demonstrated the quadratic formula and the magic potion. So for this one, we will do the factoring. It is what you should recognize, and it is the more efficient method. If you don't recognize it, then of course you can do the quadratic formula, and you can also use the magic potion on this equation as well. But we're going to factor it. So what we're looking for are the factors of 2 that by subtraction come up with 1. Well, of course, that's our 1 and 2. And our negative, in order to end up with a negative, that means we need to do 1 minus 2. So the 2 should be negative. 1 minus 2 is a negative 1. If this were positive 1, we would do 2 minus 1. So the sign is important. So when we go to do our factors, remember, every trinomial breaks down to 2 binomials. So instead of x and x, we're going to do x to the 1/3, because that's our key, and x to the 1/3. Well, if you notice, if you multiply like bases, you add exponents. 1/3 plus 1/3 is 2/3, so it checks. Okay? Now we have these. We need a +1 and we need a -2. So let's double check again. X to the 1/3 times x to the 1/3 is x to the 2/3. +1 times -2 is -2. Here we have a +1 x to the 1/3 and a -2 x to the 1/3. So we have a positive x to the 1/3 and a -2 x to the 1/3. These are like terms. With like terms, you only combine the coefficients. You don't touch the variable and exponent. You only combine the coefficients. So we have a +1 with a -2 does give us a -1. So this checks, and we now have our factoring set up. If you're factoring these kind of weird looking equations, please double check to make sure you have your signs right. I notice a lot of students factor, they have the right idea, they get the right numbers, but oftentimes they get the signs mixed up, and it's sad to see you end up with wrong answers when you have the right idea, but those little details get past you. So signs are very important. Now we use our zero product rule. So x to the 1/3 plus 1 equals 0, and x to the 1/3 minus 2 equals 0. So with this one, we move it over. X to the 1/3 equals -1. Now this is different from a square or square root kind of thing. When you're dealing with cubes and cube roots, it's a little different than with squares and square roots. For example, you can't square root a negative. You can cube root a negative, okay? So that idea of not square rooting negatives is only for even powers. With odd powers, it's not a problem. So in this case, we're actually cubing, not cube rooting. So we cube both sides. You do have to pay attention to the sign. 3 negatives is still negative. So we're going to end up with x equals -1. And when we do this over here, we get x to the 1/3 equals 2. So that when we cube both sides, notice your 3, when you have an exponent raised to an exponent, you multiply exponents. 1/3 times 3 is 1. That's what you want, x to the 1 power. So cube both sides, we get 8. So -1 and 8 are our answers. And notice we already used the key right here, so we don't have to do that again down here. We already used the key in the factoring. So these are the values of x. You can double check it if you want to. It works. But what we need is find the coordinates plural. And it doesn't mean the coordinates as in 2 x values. It's wanting the y value as well. So be careful that you're getting the complete information that it wants. So we have -1 and 8 as our x values. All you have to do is plug it into one of the originals. Don't plug it into this one here. There's no y variable here. If you plug it into here, you're just going to end up with 0. It will satisfy the equation and show that when you plug in 8, the cube root of 8 is 2, squared is 4, cube root of 8 is 2, 4 minus 2 is 2, 2 minus 2 is 0. You just end up with 0 again. You're only showing it satisfies it, but there's no y there. You need to go back up to one of these. You can either use this one or this one. Plug in, let's plug in the 8 first. If you plug in the 8, remember, just split your fraction into 2 parts. The bottom number is cube root. Cube root of 8 is 2, squared is 4, and 4 minus 1 is 3. Now, if you're not sure of yourself, just plug it in the other one. Cube root of 8 is 2, plus 1, 3. So you verify that you did it right. Now let's go to the negative one. Cube root of negative 1 is negative 1. Squared is positive 1. Positive 1 minus 0 is 0. So we end up with a 0 here. Okay? Double check. Put in a negative 1 over here. Cube root of negative 1 is negative 1. Negative 1 plus 1, again, we get 0. Remember, these coordinates have to satisfy both equations at the same time, because that is the location where the 2 graphs are intersecting. So at that one point of intersection means our coordinate works in both equations. If you need to do it like on the side like this, y equals, say, 8 to the 1/3 plus 1, y equals 2 plus 1 equals 3. You can write it out. If you can do it in your head, then that's good. You can do it in both so that you double check your mental math. But if you need to write it down and solve it, you can do it that way as well. Okay, so this is a little bit more elaborate Cambridge question type that involves reducing to a quadratic, although our reducing to a quadratic, we chose to use factoring. In the previous examples, we also used quadratic formula and the magic potion method. So you have a lot of tools at your disposal. If you learn them carefully as we go through these, this quadratic unit, each part you're learning a different tool. And if you learn each one of them very well, then you're setting a good foundation for yourself as we move forward through the Pure Maths 1 coursework, that you will succeed in the future units, because many times what you're working with, even if it's like trigonometry, will end up in a quadratic equation, but instead of x, you now have a trig function there, but it still uses algebraic quadratic methods for breaking that trig equation down. Okay, so good luck. Hope you enjoyed. Thank you for joining me, and I'll see you next time in part 5 of our quadratic series.